Welcome to The Explainer. Today, we're going to tackle something that powers literally our entire world. We're breaking down how electricity really works, from the tiniest particle all the way to the outlet in your wall.
You've done it 1,000 times, right? You walk into a room, you flip a switch, and boom, instant light. It feels like magic. But what is actually going on inside that wire to make that happen so fast?
Well, the secret isn't magic at all. It's all about controlling the flow of the universe's tiniest particles. Think of it like an invisible river. And here's the cool part. The signal to start flowing travels at almost the speed of light, but the particles themselves are part of a much more interesting sort of chain reaction.
Okay, so to really get this, we've got to go small. No, like really, really small. We're talking about going inside a single atom. This is where the entire story of electricity begins.
So, everything around us, you, me, this screen, it's all made of atoms. And in the middle of every atom, you've got a nucleus with positive protons. Orbiting around that nucleus are these teeny tiny negatively charged particles called electrons. And the key thing to remember is that opposites attract. The negative electrons are held in place by those positive protons. Now here is where it gets interesting. This is the key concept: free electrons. In some materials, especially metals like copper, those outermost electrons are kind of restless. They aren't held very tightly, so they can easily be nudged to jump over to a neighboring atom. They're the rebels of the atomic world.
Okay, so we have these restless electrons just randomly jumping all over the place. The big challenge is, how do we get trillions and trillions of them to stop doing that and start marching in the exact same direction? That's when we get electricity.
And this is exactly why the materials we use are so incredibly important. Conductors, like the copper inside a wire, are just packed with those free electrons. They're basically a superhighway for electricity. On the other hand, insulators, like the rubber coating on the outside of that wire, have very few free electrons. They hold on to them super tightly, which stops the flow cold. You absolutely need both, the highway and the guardrails, to get electricity where you want it to go safely. So, once we apply a force, we can get all those free electrons to move in one organized direction. And that organized flow, that march of electrons, is what we call an electrical current. We measure it in amperes, or just amps for short. And just to give you an idea of the scale we're talking about, just one single amp of current is more than 6 quintillion electrons flowing past a single point in that wire every single second. It's a number so huge it's almost impossible to imagine. A literal stampede of particles. An electron stampede is obviously really powerful, but how do we control it? Well, it turns out this entire flow is governed by 3 fundamental rules of the road. First on the list is voltage. The easiest way to think about voltage is just electrical pressure. It's the push or the force that gets the electrons to start moving in the first place. Without any voltage, those electrons would just keep hopping around randomly.
Next up is current, which we've already met. This is the rate of the flow itself. You know, how many electrons are actually moving past a certain point every second. It's the volume of that electron river.
And finally, we have resistance. This is basically electrical friction. As all those electrons are flowing, they bump into atoms inside the wire, and that slows them down. Now, you might think friction is a bad thing, but it's actually incredibly useful. That resistance is what generates heat, which is exactly how your toaster gets hot enough to make toast. I know, these 3 concepts can feel a little abstract, so let's use a super simple, classic analogy to make it all crystal clear. Just imagine water flowing through a garden hose. So in this analogy, the voltage is just the water pressure from the top. The current is the flow rate, how much water is coming out of the end. And the resistance? Well, that's just the width of the hose. If you squeeze the hose, you're adding resistance and restricting the flow, right? It's really that simple. Okay, so now we have the push, which is voltage, the flow, which is current, and the friction, which is resistance. Let's see how all 3 of these come together in a real working system called a circuit. Now, this is absolutely critical. For electricity to do anything useful, it has to have a complete closed loop to travel through. That's a circuit. The electrons have to flow from the power source through whatever it is you're powering, like a light bulb, and then all the way back to the source. If you break that loop anywhere, the flow stops instantly. That's what a light switch does. So, a German physicist by the name of George Ohm figured out that these 3 things, voltage, current, and resistance, weren't just random. He discovered that they're all locked together by a really elegant and simple rule. He figured out this simple equation, which we now call Ohm's law: voltage equals current times resistance. And what's so powerful about this is that if you know any two of those values, you can always calculate the third one. It is the foundational rule for pretty much all electronics.
So we've got the rules for how current flows, but it turns out that the current itself can come in two very different forms. This distinction was so important that it actually sparked the famous War of the Currents between Nikola Tesla and Thomas Edison. First, you have direct current, or DC. This is a steady, one-way flow of electrons. Think batteries, that's DC power. Then you have alternating current, or AC. In AC, the electrons don't just flow in one direction. They vibrate back and forth super fast, constantly reversing where they're going. And that is the kind of power that comes out of the outlets in your wall.
So why do we have both? Well, because they each have their own superpowers. AC is amazing for sending electricity over super long distances, like from a power plant to your city. But DC is what you need if you want to store power, in batteries. So it's not that one is better than the other. Our modern world literally needs both of them to work. With all of this invisible power flowing through our walls, we obviously need some pretty good safety systems. So what happens when that powerful flow of electrons goes wrong? Well, there are two main ways things can go bad. The first is an overload. That's like a traffic jam. You plug in too many things at once, and they try to draw more current than the wires can handle. The second is a short circuit, and that's even more dangerous. That's when the electricity finds a shortcut that bypasses all the resistance, causing a huge, sudden surge of current. And this brilliant little device is what protects us: the circuit breaker. During an overload, that extra current heats up a special strip of metal inside. As that strip gets too hot, it physically bends, and that bending action trips a switch, which instantly breaks the circuit and stops the flow of electricity. It's a simple, genius, and totally automatic safety guard for our homes. So when you think about it, from the tiny jump of a single electron to the gigantic power grid that fuels our entire civilization, electricity is really just the story of us learning to harness an invisible force. We learned to control the electron. It really makes you wonder, what invisible force will we master next?